In the next subsection, we'll see one concrete example for a problem that is in general NP-hard, but admits such a pseudo-polynomial time algorithm, which indeed has practical value, because sometimes in these problems the integers that occur are indeed not too big. That's the knapsack problem. So just to recap, we've seen the decision version. The optimization version is given here again. We have these items, 1 up to n. And what we're given is the weights, which is a negative thing if you want, and then values, which is the positive thing, and some capacity. And you're trying to select a set of items, T, so that their total weight is at most B. They fit into your knapsack. It's also called the burglar problem. You're breaking into a house and you're trying to take as many valuables as you can fit in your backpack before you have to run. But if your backpack's too heavy, you can't run fast enough. Let's stay with the more neutral formulation. So you just take items of total weight at most B, but you want to maximize the value you get for them. Okay. Let's recap what dynamic programming is, just to put that in context. This is mostly for people that have seen this template in efficient algorithms. A reminder, if you've seen dynamic programming somewhere else, then you may have seen it in slightly different terminology. The essence of dynamic programming is to break a problem into small subproblems that you exhaustively solve, but where you can reuse solutions of subproblems to stitch together a solution for a bigger problem. And then there's the bottom 3 steps are very mechanic. They're always the same. So just on this concrete example, for the knapsack problem, what we can use as subproblems is restricting to the first n prime items. Instead of allowing all of them, we just look at a prefix of the items. And we also restrict the weight to be potentially less than the total weight we are allowed in the end. And then at each point in time, we'll make a guess whether or not we include this last item that we are allowed now. And that will be enough to write down a recurrence. So let's do that together. V stands for value. It's going to be the maximal value you can get in this subproblem, meaning you can only pick items up to position n prime. You're only allowed the first items, and the weight is further restricted, not B, but B prime. So we'll need some base cases. Let's see if I can fit that here. We can do the idiotic base case when n prime is 0 and I'm not allowed any items. Then the maximal value has to be 0. That might be all base cases we need, really. Let's see. If we're allowed one item, at least one, then there's 2 options. Okay. If we have, if the new item n prime fits in our knapsack, then we have the option of taking it. If it's too big, then we don't even have this option. Let's do the simple version first. And then this will be the more interesting case. So if the item n prime cannot fit in, the best I can do is to use any of the previous items. And I'm still at full capacity. I can take the same capacity, it doesn't matter. Now, if I can fit this last item, I have 2 options. I can pick the best of 2 choices. So I'm doing a maximum. And one option is the same as above. I'm not picking this new item that I'm allowed now. So again, this option. But here I have the second choice of picking this new item. So I get the value for n prime. But then for the rest of the items, I only have b prime minus the weight of this. So I have a smaller leftover capacity. I have a smaller leftover capacity, whatever is left after putting this item in, but I get the value for this item. With this recurrence, the final answer will just be in the original problem, where I'm allowed all items and the full capacity. And you can recursively fill those. This is the point where it makes a difference. If you've seen DP before, you'll say, yeah, I know I can take it from here. There's a bottom-up algorithm to fill a table of all those V entries, and I know how to backtrace, and you can reconstruct the solution. If none of this makes sense, then suffices to say that you can evaluate this recursion, and whenever you use a value recursively, you store it in a lookup table, so that you're never computing the same value again, which means you're only going to spend constant time evaluating any of these options when you first evaluate them. Now, constant time is the number of arithmetic operations. On a Turing machine, it would be log max int time. So let's analyze the running time. So to compute these options, in particular compute the max and the plus, log max int. Because these are numbers with that many bits, and you have to add them up on a Turing machine. We're in this logarithmic cost model. That's for one of these entries. And the number of entries in the matrix is the overall number of items, and the overall number of entries for the second component is the budget. And now the number of items can be bounded in terms of the size of the input, but B is a number that I'm specifying in the input. N is bounded, the items are bounded by the input size because I have to list a number for each of them. So I need to spend at least n bits to specify n items. But for this number B, the capacity of my knapsack, this I can just write down as a binary number. So this will be another factor. And here it's just max int. That's the best we can say in general. So in particular, this is the pseudo-polynomial part, that we have to fill this table for all possible capacities between 0 and b. All right. Here's summed up what I've briefly sketched. The running time for this dynamic programming algorithm is polynomial in the input size and max int. And so it's a pseudo-polynomial algorithm. But you may also know that the knapsack problem in general is NP-hard. So it is one of those cases where we shouldn't expect a polynomial time algorithm, but a pseudo-polynomial algorithm is possible. This is one concrete example where this theory seems to have value, and if indeed your capacities are small, then that's good. Also, let me point out this is a bit pessimistic in that sense that we don't care how big the values are. It's only the weights that matter, or the capacity of the knapsack. If the values are big, that's not a problem. We just compute with them and add them up. The capacity is what blows up the space of this dynamic program. So just to stress that point, that might be, in an application, this might make a difference. Now we've seen one concrete example. You can apply a very similar trick to some other problems, which admittedly are somewhat similar to Knapsack. There's the partition problem. Remember, these are numbers. Can you assign them to two camps so that their sum is equal? Or making change, if you have coins and you're trying to give the smallest number of coins to make a certain total. Finding the minimum number of coins is NP hard, but can be solved with such a pseudo-polynomial algorithm. But they also have a similar flavor to this knapsack problem. Whereas for other problems, even if they're integer input problems, it seems you cannot do such an algorithm. And there's a little bit of theory to suggest why that is indeed not possible.